Hey everyone, and welcome to this explainer. Today, we're unlocking one of the absolute most powerful concepts in modern programming, C++ classes. If you've ever looked at your code and thought it was getting a bit messy, or if you've been searching for a way to perfectly model real-world objects in your software, you are exactly in the right place. We're going to demystify the core object-oriented features of C++ today, and we'll do it using a really simple, relatable blueprint metaphor. We are skipping the confusing jargon so you can see exactly how C++ organizes code to make your life as a developer infinitely easier. Here's what we're covering today. We'll start with an intro to C++ classes, look at public versus private data, unpack constructors and destructors, figure out what the this pointer actually is, explore operator overloading, and wrap it all up with modern memory management. Let's get right into it. Welcome to C++ classes. All right, so to really get C++, you have to completely separate the idea of a class from the reality of an object. Think of a class as your master blueprint. It's literally like a recipe for a perfect cup of masala chai. The recipe itself, well, you can't drink it, right? It just sets the rules, the ingredients, and the steps. An object, on the other hand, is the actual instantiation. It's that piping hot, physical cup of chai that you can actually hold and drink. In programming terms, defining a class just sets up the rules for how something should look and behave. It doesn't actually take up any space. It's only when you create or instantiate an object that the compiler actually carves out memory space for it. Now, this concept is a massive upgrade from the old days of C. In legacy C, structures were basically just simple boxes holding plain data elements, like integers or characters. But a C++ class? Totally different beast. It holds both the data and the functions that operate on that data. It ties them together into a single unified entity. So your data and the methods that manipulate it are finally living happily under the exact same roof. Moving on to Section 2, public versus private data. So now that your data and your functions are roommates, you kind of have to decide who gets to see what. In a standard C struct, every member is public by default. Literally, anyone can access and change anything. But in a C++ class, things are locked down. Members are private by default. Unless you explicitly use the keyword public, the outside world cannot touch the internal data of your class. This is exactly how C++ protects its data, and it's a huge leap forward from those older, more vulnerable structures. We call this data hiding. And look, don't confuse this with cybersecurity. Data hiding isn't about stopping malicious hackers. It's honestly just about protecting well-meaning programmers from making honest mistakes. Think of private data exactly like your UPI PIN, only you should have direct access to it. You definitely don't want anyone just reaching in and randomly changing your bank balance. Public functions, meanwhile, act like the ATM interface or your banking app. They give the outside world a safe, highly controlled way to interact with that private data. You ask the public function to make a withdrawal, and the function safely checks your private balance behind the scenes to see if it's allowed. Which brings us to Section 3, Constructors and Destructors Explained. Okay, so how do these objects actually come to life? Enter the constructor. A constructor is a special member function that boots up your object the exact second it's created. And there are some unbreakable rules here. First, it has to have the exact same name as the class itself. Second, no return type, not even void. It doesn't return a thing because its only job is initialization. And finally, it executes automatically. This is literally how the compiler knows a member function is actually a special constructor. It sees that matching name and the missing return type and just knows what to do. But hey, you aren't limited to just one single way of building an object. You can use overloaded constructors. This just means you can write multiple constructors inside the same class. Maybe you have a 0-argument version that just sets some default values, and a 2-argument version that lets the user pass in very specific data. The compiler is smart enough to trigger the correct one based on how you define the object in your code. Oh, and a quick side note, if you don't write any constructor at all, the compiler will quietly build a hidden, implicit 0-argument constructor for you, just to get the job done. Now, what goes up must come down. Just as a constructor brings an object to life, a destructor cleans it up. The lifecycle is super straightforward. The object is created and the constructor fires. Then your program runs and does its thing. Finally, when program control exits the current scope, like when a function finishes running, the object is destroyed and the destructor fires completely automatically. Destructors share the exact same name as the class, just like constructors do, but they have a little tilde symbol right in front of them. They take no arguments, return no values, and their main job is just to deallocate any memory the object grabbed during its lifetime. But wait, This brings up a really fascinating question. Imagine you have three different rectangle objects, and they all call the exact same public calculate_area function. How does that single function know which rectangle's length and breadth to look at? How does an object actually know its own memory address inside a shared function? Let's find out in Section 4, Understanding the This Pointer. The answer is basically C++ magic happening behind the scenes. Every single time an object calls a member function, C++ secretly passes along a hidden pointer to that function. It is literally called the this pointer. It's a special pointer accessible by every member function, and it holds the exact memory address of the specific object that called it. So the second that function is invoked, this just pops into existence, holding the caller's address. It's basically a phantom argument that you never even have to type. Because of this hidden pointer, when your function says give me the variable called real, the compiler translates that internally to this arrow real. It's explicitly telling the compiler to look at the real variable belonging to the specific object sitting at that exact memory address. You can even manually type this arrow in your code if you want. It acts like an object pointing a finger at its own internal data, which is incredibly useful if you ever need an object to return a value of itself. Moving right along to Section 5, the power of operator overloading. Now, this is a feature that truly makes custom C++ objects feel like native built-in parts of the language. Operator overloading simply means teaching standard C++ operators, like the plus sign, the equals sign, or the increment operator, how to behave when they're used on your complex custom objects. Think about it. Instead of writing a clunky function like add complex numbers, wouldn't it be beautiful to just write C3 equals C1 plus C2? By overloading the plus operator, we define exactly what happens when two custom objects are added together, and it makes our code so incredibly clean and readable. And here is a brilliantly quirky part of C++. When you're overloading the increment operator, you actually have two versions: prefix, where the pluses come first, and postfix, where they come after. To tell them apart, C++ uses the strangest little trick. For the prefix version, you just write empty parentheses, but for the postfix version, you put the word int inside the parentheses. Now, that random int is absolutely not an integer argument you're passing. It doesn't mean integer at all here. It's literally just a secret dummy signal to the compiler that says, hey, create the postfix version of this operator. Pretty wild, right? Finally, let's wrap things up with Section 6, Modern Memory Management. C++ gives you incredible control over dynamic memory. That's memory allocated on the fly while the program is running. And it does it so much more elegantly than legacy C. In the old C days, you had to use these clunky functions called malloc and free, pulling from the system heap. It required super annoying typecasting because malloc just grabbed a blind chunk of raw bytes, and you had to calculate the exact size yourself using sizeof. But modern C++, it introduces the new and delete operators, pulling from a pool called the free store. The absolute beauty of new is that it allocates the proper size automatically based on the data type you give it, completely removing the need for messy typecasting. So managing this free store is a total breeze. You just use the word new, followed by your data type. It allocates the precise amount of memory needed, fires off any constructors automatically, and then assigns that address straight to a pointer. When you're all done, you simply use delete on that pointer. It fires the destructor and safely returns that specific memory back to the free store. Because new and delete associate the memory allocation directly with the data type we're using, they work absolutely flawlessly with our custom classes. But okay, I have to issue a serious disaster warning right here. If you're allocating an array of objects, let's say 30 integers, using new with square brackets, you absolutely must use delete with empty square brackets to free it. If you forget those brackets and just use standard delete, the compiler might not even flag an error, but it could silently corrupt your heap. In a lot of compilers, standard delete will only destroy the very first object in the array, leaving the rest completely stranded in memory as a leak. Always remember, if you create an array of things, you have to tell the compiler you're deleting an array of things. And that brings us to the end of our journey through C++ classes. We've covered how classes act as your master blueprint, how to protect your data like it's a UPI pin, the whole life cycle of objects, the phantom magic of the this pointer, and how to cleanly manage your memory. You now literally hold the ultimate blueprint in your hands. So the real question is, what kind of incredible, scalable software are you going to build with it? Let that sink in, keep coding, and I'll see you in the next explainer.